Trigonometry literally means triangle measure. And we're going to be looking at right triangles for right now. Now, triangles are one of the most basic shapes you can have. You can't really have a shape with two sides, but three sides is when you get an interesting two-dimensional shape. For this triangle, for any right triangle really, we can name an angle and name the sides based on that angle. So first off, naming the angle, we typically like using the Greek letter theta, which is an O with a line through it. That's what this symbol is here, even though it's hard to see. This is really the standard variable given for an unknown angle. Really, like how x is given for an unknown variable, some unknown number that you don't know for an equation. Theta is what's the variable given for an angle measurement. And it's important to note that theta is normally designated as an angle. So if you see it, you should kind of think of it as an angle, not as just a number. Now, the side opposite this angle, if you go from this angle and you just draw a line out, the side opposite this is going to be labeled O for opposite, of course. The side next to it is labeled A. You don't label this side A because this side is opposite the 90-degree angle, and that is always the hypotenuse. So it's the angle that the side that's adjacent to the angle that's not the hypotenuse, that's labeled A. So we have theta, the side opposite, the side adjacent, and the hypotenuse. And with this information, we can now define the 6 trig functions. The first basic 3 are the sine function, written as sine theta equals opposite over the hypotenuse. It's the ratio of the length of the opposite side divided by the hypotenuse of that right triangle. The cosine function is going to be the adjacent side length divided by the hypotenuse length. And the tangent function. The tangent function is going to be opposite over adjacent. And one of the best ways to memorize this is using this mnemonic, SOHCAHTOA. So is sine equals opposite over hypotenuse. Ka is cosine equals adjacent over hypotenuse. And toa is tangent equals opposite over adjacent. That's how you can memorize this. Of course, from these are all fractions, and a lot of times we use the reciprocals of these quite frequently. And that gives us the last 3 common trig functions. These are not used as commonly as sine, cosine, tangent. Definitely not as much as sine and cosine. But they are there, and it's important to know them. We will be using them. The first one is called cosecant. That's labeled CSC. And that is the flipped version of sine, right? Sine theta equals opposite over hypotenuse. So if you flip that, you get cosecant, the hypotenuse over opposite. So really, you don't need to memorize what is cosecant. You need to memorize what is sine. Sine is the so in SOHCAHTOA. And then you have to memorize, well, sine corresponds to cosecant. Why does it correspond to cosecant? I'll show you that why in a second. Now, secant is the next one, and this corresponds to the flipped version of cosine. So we have cosine is adjacent over hypotenuse, the ka in SOHCAHTOA. And if you flip that, you get the secant. Of course, I can just write this as 1 over cosine of theta equals secant of theta. Just like in this first one, I could write 1 over sine theta equals cosecant of theta. And finally, we have cotangent. This is the flipped version of tangent. And so we get tangent, as you can see above there, equals opposite over adjacent. So cotangent is going to be adjacent over opposite. So tangent and cotangent are fairly obvious because they're, tangent and cotangent. The reason why sine goes to cosecant and cosine goes with secant, is just based on a naming convention. If you label the other angle phi, which is another Greek letter, and you look at the trigonometry on theta and phi, you're going to see there's a lot of similarities between them. Of course, it's the same triangle, so there's going to be. And as I show here, this is the relation that sine of theta is the same as 1 over secant of phi. So it's a different way of thinking about how you define the trig functions, and this is the standard way of doing it. It's going to be hard at first, memorizing that cosecant is the flipped version of sine, but eventually you'll understand that. Now, whenever we have a triangle, we really want to know about all of its properties. And if something's unknown about the triangle, we really want to find it. That's what's called really solving a triangle. So it's where you know everything about the triangle. And here we know a few pieces of information. It's a right triangle. It has a side length of 4 here and an angle of 20. So this angle is going to be our theta, which makes 4 the opposite of theta. We do not know what this angle is. We do not know what this side is. This is going to be our adjacent side. And we do not know what the hypotenuse is. But we have everything we need to find the rest of it. First off, we can find this second angle quite easily, right? We have a 90-degree angle, a 20-degree angle, and triangles have the property that all the angles added up must equal 180 degrees. So 180 degrees equals 20 degrees plus 90 degrees from the right angle plus this unknown angle. I'll name it phi here. Plus phi. That's 110. Subtract that over. We get phi equals 70 degrees. So this has to be 70 degrees here. Okay. Now, using this information, we can find the hypotenuse and adjacent by using the right triangle trig. So first off, we have sine of theta. I don't have to actually use theta. I can just use 20 degrees. But sine of this angle is going to be opposite, which we know is 4, over the hypotenuse, which we don't know. But we know what sine 20 is. That's you can type it in a calculator. I'll give you a decimal number. And we know what 4 is, so all we have to do is solve for h. I'm going to multiply h over, and then divide by sine 20. And that gives us that h equals 4 over sine 20, 20 degrees. It's important to note that in calculators there's a setting between degrees and radians because there's, both are used with some frequency. So make sure your mode or your setting on the calculator is in degrees for this case, since we have 20 degrees already. You should see DEG or D instead of RAD or R. So we go 4 divided by sine 20. And my calculator says that's going to be 11.70 approximately. Okay, now I can find the adjacent side. And whenever you're doing this, you should always use information given, not information you found. So instead of using the hypotenuse that I just found, I'm going to find a trig function that does not use this because I don't want to use this approximation in solving the next one because that just further makes a worse approximation. If you keep using approximations in your mathematics, eventually you're going to be so far off that it's not going to be the correct answer here. So instead, I want to use tangent. Tangent of theta, or 20 degrees, equals opposite, which is 4. That's the one that we were given. We know it's 4, over adjacent. I did not use hypotenuse because that's an approximation that I used. I wanted to use the 4 and the 20 that was given. Okay. Doing a similar process, I get A equals 4 over tangent 20. And plugging that in my calculator, I get approximately 10.99. And now my triangle is solved because I have all the sides known and I have all the angles known. And with that, we can see what are the 6 trig functions for the angle 20. We know sine 20 equals opposite over hypotenuse. Cosine of 20 is adjacent over hypotenuse. And the tangent of 20 is going to be opposite over adjacent, just using SOHCAHTOA. The other 3 are just the flipped versions of these. So sine goes to cosecant, remember that? So cosecant of 20 is just the flipped version of sine, so 11.70 over 4. Secant is flipped of cosine, 11.70 over 10.99. And cotangent is the flipped version of tangent, so 10.99 over 4. And the importance of this is that if you type this in a calculator, sine of 20, it should be very close to what you would get if you type this into a calculator. It should give you the same number almost. Of course, it's going to be an approximation since I use 11.70, but it should be very close. Okay, here we have an antenna on top of a building, so I'll just draw a building here. And then I'm going to draw an antenna like this, I guess. Something like that with a little ball on top. And we know that from a location 300 feet from the base of the building, so my building's not quite great. Let me just do it like this. So 300 feet from this base, let's say this position here, so this right here is 300 feet. The angle of elevation to the top of the building is measured to be 40 degrees. So this angle here, let's see if I can get it just about there. This is 40 degrees. And from the same location, this same vertex here, the angle of elevation to the top of the antenna is 43 degrees. So if we go all the way to the top of the antenna, this angle is 43 degrees. What's the height of the antenna? Well, what we need to know is this distance here. That's what we're looking for. But we have 2 triangles here. We have this big triangle. I'll draw it like this. The big triangle has 43 degrees. This is the building side, and this is 300 feet. That's still constant. And you have this smaller triangle. Both of these are right triangles as well, I should say. This smaller triangle is, I'm just exaggerating a little bit in my drawing, is 40 degrees. This is still 300 feet, and this is still a right triangle. And all we need to do is figure out what is this height, because this height is the top of the antenna. And what is this height? This height is to the height of the base of the antenna, right? The base of the antenna is at the top of the building. And the distance between this height here and this height is your desired distance. So if you find that side for both triangles, then subtract them, we should be good to go. And we can do that with right triangle trig. We have the opposite side of 43, that's what we want to know. This is what we want to know here, and what we want to know here. Both of them are opposite the angle. And we have the adjacent side to that angle. So we want to know the opposite side, and we have the adjacent side and the angle. So if you look at SOHCAHTOA, this is one simple way of doing it. We have the angle, so I can already check above sine, cosine, tangent, because I can find those. We want to know the side opposite, so I'm going to put that with a check mark above the O. And we also know the adjacent. So we have the adjacent there and the adjacent there. And that tells me that I want to use tangent because I have all 3 pieces of information for that trig function. Okay, so for this first one, I get tangent of 43 equals TOA is opposite over adjacent. Opposite we don't know. I'll write this as, let's say, H1. Adjacent is 300 feet. And for this one, we have tangent of 43. I'll name this one H2. Opposite over adjacent. And now I can find H1 and H2. I'm just going to multiply 300 over. So I get 300 times tangent of 43. Tangent of 43 degrees. It's going to be 279.75 approximately. And H2, I'll multiply 300 over and get 300 times, sorry, this one's supposed to be 40 degrees, not 43. Tangent of 40 degrees. That's going to give me 251.73. So our desired distance x is just the larger height, which is h1, minus the smaller height, h2. And doing that, we're going to get, let's see, I think it's 28.02. 28.02 feet. Of course, this is all approximate because we did the tangent, and that has to be approximation. But that is approximately how tall the antenna is. Give it a try in number 5. Now, there are two special triangles we're going to use quite frequently in trigonometry. We've actually already seen these angles in the previous part of this this video. And these are going to be the 30, 60, 90 and the 45, 45, 90. So 30, 60, 45, and 90, these were all the special angles that we had seen, right? This is going to be pi over 6, pi over 3, and pi over 2. This one's pi over 4, pi over 4 again, and then pi over 2. So those are the special angles. And really what's interesting about these is they have unique side lengths. So if this is a 30, 60, 90 triangle, then the side opposite the 30 is going to be x. The side opposite the 60 is going to be root 3 times x. And the hypotenuse is always going to be 2 times x. It's always going to satisfy these ratios. For the 45, 45, 90, the sides opposite the 45s are going to be the same, so they're the same angle, x and x, and then the hypotenuse is always going to be root 2 times x. If x equals 1, of course, that means we're going to have 1 here. Then root 3 times 1 is just going to be root 3. And 2 times 1 is going to be 2. So 1 root 3, 2. Square root of 3 is about 1.73. It's between 1 and 2. And the angle 60 degrees, which is opposite the root 3, is between 30 and 90. So that makes sense. If x is 1 here, we have 1, 1, and then the square root of 2. These are the important ones to keep in mind. We're going to be using these a lot, as I said before. And of course, we can do the 6 trig functions on these angles, or these triangles. And what's nice is that they simplify down to these nice forms. So first off, for the 30 degrees, right? If I take sine of 30 degrees, I get opposite over hypotenuse. So x over 2x, of course the x's cancel, and we get 1/2. So sine of pi over 6, or 30 degrees, same thing, is 1/2. And you can do the same process for all of these things, and you get these interesting answers here. We get 1/2, root 3 over 2, root 3 over 3, 2 root 3 over 3, and then root 3. Of course, I rationalize the denominators here. That's an important thing to note, that whenever you have a denominator of radical, rationalize it. 60 is very similar. And then the 45s always have this root 2 over 2 in them. And we get 1 for tangent and cotangent, and then root 2 for the cosecant and secant. That's because the 45s had the same side lengths, x and x, so that's why there's so many similarities there. But these are very important, and you're going to see them a lot when you're working through trigonometry in general. So if I were to ask the question, what is this expression here? Really all we have to do is figure out what is each one of these special trig portions. So what is cosecant of pi over 6? What's secant pi over 4? What's sine of pi over 4? And you should really memorize each one of these things. They're not really that hard, because once you get an idea, of how these functions work with the unit circle, which we're going to look at pretty soon, then these things will become a lot clearer how to memorize them. Really only these first three are what's necessary. These last three are just a reciprocal of the first three. So cosecant of pi over 6, you could just go up to, cosecant of pi over 6 is just 2. So you could do it that way. Once you memorize it, of course, you'll be able to do it. Secant is the flip of cosine. Cosine of pi over 4 is going to be root 2 over 2. So the flip version of that is going to be 2 over root 2. Of course, you're going to rationalize that. So you're going to multiply the top and bottom by root 2. That's going to end up giving you just root 2. And the secant of pi over 4 is just root 2. So yeah. Sine of pi over 4 is root 2 over 2, which is, right there. And we simplify this down. We're going to get 1 plus root 2. The bottom is a fraction, so I'm going to multiply by the reciprocal. That's going to give me 2 plus 2 root 2 over root 2. Rationalize the denominator. And we get 2 root 2 plus 2 times 2. The root 2 and the root 2 make just 2. And on the bottom we get 2. 2's cancel everywhere. We get root 2 plus 2.